Okay, so we're going to go over example 2 on lecture number 9. So the idea of this example is that we have an infinite sheet of charge, and the infinite sheet of charge passes through the point y equals -2. So it's, if you think about it, it's parallel to the xz plane, right? Except it's bumped back 2 spots along the y-axis and still parallel to the xz plane. So the question is, what is the electric field intensity seen at the point 0 for x, 2 for y, 1 for z? So remember, we found the formula for an infinite sheet of charge, and that formula is equal to the surface charge density divided by 2 times the permittivity of free space times a vector in the normal direction. So all we need to find is what is a vector in the normal direction and a unit vector of length 1. So what we need to do is find the vector that points from here to a point on the plane. So obviously a normal vector is going to be horizontal from the plane. Well, it's easy to see here that a vector in the AY direction is going to be normal to the plane, right? We have 2 normals here. We have AY and -AY pointing the other way because it's parallel to the XZ plane. Okay, so that's the first step. Find that normal vector, right? And we say that the AY vector is the normal vector. So from that point, it's pretty simple. It's just a simple plug and chug problem. We see that rho sub s is given in the problem, which is 10 nanocoulombs per meter squared, and we already have the normal vector and the other 2 components are just constant, so we can then calculate what the electric field intensity is. So it's going to be 10 times 10 to the -9, that's coulombs per meter squared, 2 times the permittivity of free space, which is 8.854 times 10 to the -12, and that's going to be in the AY direction, okay? And whenever we calculate that out, we get 564.7 times AY, and that's electric field intensity, so the units are volts per meter.